Okay, so there's the program. And as usual, the first 4 lines always look the same. We import Floyd's proof automation system. We import the abstract syntax tree of the program that was parsed by CompCert's front end. And we ask the tactical system to make some calculations about struct definitions and global variables. Now, when we do proofs about C programs, we prove that they relate to some functional model of what we're doing calculations about. And the functional model is in the mathematics of your application domain. So here's our functional model of adding up the elements of an array. It's just a fold right of integer add with base case 0. All right, so the functional model of our application domain is not too complicated for this example. And then you prove some properties of your functional model. So here's a property of interest here, that sum z over the concatenation of 2 lists is equal to the sum of the sum z over each of the individual lists. And you prove that. Sometimes your application domain is mathematically more complicated, and the proofs there are non-trivial, but this one was pretty easy. Okay. Then we specify, this I call the API spec. API, the application programmer interface, is how you interact with the program. Well, how do you interact with the C function? You pass it pointers to data structures that are in memory, and you get back results that are data structures in memory. So what we have to explain now is how the functional model of the program that we defined up there relates to the data structures in memory. That's the API spec. And one hopes that this part is not mathematically too complicated. If there's interesting math to do, put it up here in the functional model. Don't mix it too much with your C program specification. All right, so here's the sum array function. Remember, it took a parameter a that's the pointer to an array, so that has C language type pointer to unsigned int, and an n that is a signed int. And the spatial part of the precondition says there's a data at, so there's in memory at address a. What is a? It's the contents of the C variable written underscore a. In memory at address A with type array unsigned int of this many elements, there is this value. So what is contents? It's an array of z, a list of z. Map int.repr contents smashes those mathematical integers into the 32-bit representation, and then map vint injects all those into the CompCert value type. So that's the contents of the array. And the type of this has to match the rep type function applied to the value of this one. So that's fine. That's what we expect in the precondition. There's an array with a certain contents. And the contents is a sequence of integers. We have that the n parameter contains the value size. Size is an integer, and we represent it as a 32-bit 2's complement thing. Okay. What else? Size has to be representable as a signed integer. Otherwise, here, when we smash it into 32 bits, it doesn't represent what we thought. Let's see. This adding up the elements of an array should work for read-only data just as well as it works for read-write data. If we're doing concurrent programming, for example, and we acquire some lock that gives us only shared read permission to some thing, we should still be able to do adding up the elements. So we have an arbitrary permission share here that's quantified in the with clause, but we have in the precondition that that share has to at least give read permission. What else? Well, every element of the contents array, we've we've specified here contents as a list of mathematical integers. And here we've smashed the contents into a list of 32-bit 2's complement signed numbers. So we would like to think that when we do that, we get the values we expected. And that will be true if every element of contents is in the range 0 to max unsigned. So that's one choice for the description of this function spec. Another choice that would have worked well, I think, is making this a list, explicitly a list of 32-bit 2's complement signed integers. Okay? And then we wouldn't need this because that would sort of be guaranteed. And we wouldn't need this map int.repr because it would already be a list of 32-bit signed integers. And that's a reasonable choice also for the specification of this function. I chose this way here just because maybe the user, in the user's use of this function and how the user thinks about what this function does, is thinking about integers and not 32-bit signed stuff. Okay, that's the precondition. Postcondition. Well, the array is still there. It's the same as it was before. And the return temporary contains a representation of some z of contents. So here, we've proved that the C function is a refinement of a pure function in Galena, right? That the imperative program implements a functional program. And here's the functional program it implements. This is very typical, that we have some data in the precondition, and in the postcondition, we say, oh, we computed a pure mathematical function on that data, and now we represent the result of that somewhere in the variables or memory that's described in the postcondition. So the job of the API spec is to relate pure mathematical calculations to C data structures. Okay, let's talk about the specification of the main function. This is int main avoid, so in this case there's no parameters to the function to describe here. And this main pre takes as an argument the program. This is the abstract syntax of the entire program as calculated by the parser of CompCert. And what's in the program is a lot of global variables. And any of those global variables that point to memory, well, that memory is a resource that has to be in the precondition of main. Because it's, and you need to describe in the precondition of your function the memory footprint of what you're going to operate on. And the contents of all those external initialized global variables are in there. So main pre looks at the global variable declarations in the program and calculates that for you. The postcondition of main can be anything you want, because once main returns, the program is not going to execute anymore. But here we've specified that the exit code returned by main is actually 1 plus 2 plus 3 plus 4, which if you think about that external global variable called for, F-O-U-R, that's what was in there, and that's what's going to be added up. Okay, so there's our specification. We calculate gprog, sort of the global function spec context. It'll have in it the sum array spec and the main spec and various things in the library. And these specifications are going to be put in the delta that's used in ordinary Hoare logic judgments. And when we get to a function call, and you call some external global function, and you can use the specification in delta to understand what it does. So when main calls, the sum array, yes, when main calls sum array, and we need to prove that that function call does something or other, that's when this specification in gprog will be used during the proof of main. Okay, vprog was calculated automatically up here, and it's calculated from the external global variables. Its type is var_specs. var_specs is just list of ident cross type. This is a lowercase t type, a C language type. And if we see what's in vprog, we can see that the identifier 4 has type array 4 of integers, unsigned integers. Okay, so now we're ready to prove the function. We're going to prove that the function body, f sum array, satisfies the function spec, sum array spec. And that's the same as proving this Hoare triple. The precondition from the function spec, the function body, which starts with I gets 0, and some postcondition that's abbreviated up there. So let's do forward symbolic evaluation through I gets 0 and through S gets 0. And now the current precondition for the rest of the function body says everything it said before, and S equals 0, or S contains 0, and I contains 0. Or rather, here's the mathematical integer 0, here's the 32-bit signed 2's complement integer 0, or no, this one's unsigned, and here's the C value. All right, so here's our loop invariant. Loop invariant. At each iteration, there's a value I that's the current value of the C variable I. And I is between 0 and size. Size, where did we get size? It came in as the value of the function parameter n. N contains the value size. That's part of our loop invariant. S contains the sum of this list of mathematical integers, the sublist of contents from position 0 to just before position I. Okay, so at each iteration through, we've calculated the sum of a longer sublist. And in memory, we have the entire array at A with its contents of the entire list. So that's loop invariant. And when we go forward while through a while loop, we get these 4 proof goals as usual. And the first one is to prove that the current assertion satisfies the loop invariant. So we need to demonstrate that there exists a value I such that, for example, the variable I contains the value I. Right now the variable I contains 0, so 0 seems like a good choice. And now this is the entailment we need to prove, and we ask the entailer solver to prove it, and it says proved. Okay. Second, we need to show that this expression, this is the while loop test. It's, what was the while loop test in the program? It was while I is less than n. Well, we need to show that this evaluates without crashing. What do we mean to crash? Well, if I were not initialized, or if n were not initialized, then it would crash. If we did arithmetic, we'd need to prove that it didn't overflow. Comparisons can't overflow. So really, there's not much to test here except that I and n are both initialized. And we could calculate that automatically from these 2 facts in the precondition, that I has that value and n has that value. And so the entailer bang calculates that for us. All right. Now, we need to prove that the loop body preserves the loop invariant. Okay. So here's the first command in the loop body. T prime 1 gets A sub I. Where'd that come from? Let's look at the program. S plus equals A sub I. This is a memory dereference. So in separation logic, we can reason about memory dereferences by saying, well, if there's a maps to in the precondition whose, that at address A sub I maps to contents whatever, and we do the load, then we know what values in the local variable in the postcondition. But in separation logic, reasoning that way, it's inconvenient to deal with more than one load in the same expression. And especially nested loads where I say P arrow, foo arrow bar, right? A whole nested series of loads. So for simplicity of reasoning, we want to program in a sub-language of C where sub-expressions don't contain loads and stores. No assignment statements in sub-expressions, no nested loads. We can have one load per right-hand side, but then let's put that just into a local variable. Let's not add it to another expression. So the C LightGen utility that comes with CompCert factors your C program command into, if necessary, 2 or 3 commands that have that property. And so if we look at the program where we are right now, it says T'1 gets A sub I, and then S gets S plus T'1. And this second command is just a pure calculation about local variables that doesn't access memory at all. Okay, so let's go forward through T'1 gets A sub I, and this fails. And the failure message says, I couldn't prove that your subscript was in range, in bounds, right? If you access an array outside where you have permission, then that's undefined. Now, where does the C language say you have permission? Well, the fact that access outside an array could give you a segmentation violation in C is really just a failure of the operating system to provide a complete address space for you. Okay, that's not quite what I meant. What I mean is the C type system doesn't exactly know what you have. At runtime, we have something or other. What you have permission for is what's shown in the precondition of your separation logic Hoare triple. I have permission at address A for as many elements as the length of this list. And the value of the expression underscore I, well, that evaluates to this number, I, just by this part of the precondition. And the forward command says, I couldn't prove that I is between 0 and the length of, this list. So it says, make sure listsolve or auto can prove this. Let's make sure auto can prove. Well, okay, we can do this assertion. We're going to assert that the length of contents equals size. If we could assert that, put that above the line, then try this forward command again, then it will work. Okay, so let's do this. Let's assert Z length contents equals size. Now, what do we have above the line that could prove this? If you look above the line, we know that every member of contents satisfies something, but we know nothing else about contents. There's nothing above the line that will allow us to prove that. So let's look again at this proof obligation. There's something in the precondition that will allow us to prove that. The data at can only be satisfied if the length of the contents is equal to the size of the array. That's just a consequence of data at. But this data at is not above the line. And we can't put that data at above the line because it's a predicate on memory states. And we won't have a memory state until we run the program. We certainly don't have one now. Okay, so we can use assert prop. Assert prop says, if you can prove this as a consequence of the precondition, then you're entitled to put it above the line. So we'll do assert prop. And that says, okay, prove this entailment. Here is your precondition. Here's the thing that you asserted. If you can prove this entailment, then you get to put that proposition above the line. So let's use entailer to prove it. Entailer says, okay, well, I can almost prove it, but this is what remains as the proof obligation. I'm using Z length here. Z length takes the length of a list, but gives you a Z instead of a nat. Why is that? I'll talk about that more later, but mainly because nat